Okay, is this recording? Yes, so it's my pleasure again to introduce the final speaker of the term for SPAAM. And so we all know him, right? So the speaker is Jaro. He's a third-year PhD student, final year MASDOC, and he's going to be talking about exact MCMC inference for Wright-Fisher diffusions. So Jaro.
Right, thank you. Thanks all for tuning in. So I'll be talking about some work I've been doing over the past couple of months now. And this regards doing exact inference, specifically via the machinery of Markov Chain Monte Carlo for diffusions in genetics, and in particular, that means the Wright-Fisher diffusion. This is all work that is supervised by Paul Jenkins, Jaro and Dario Spanon, and they're all at Stats. Right, but before we start, okay, still got it. Nice. This is perhaps one of my favorite pictures, so I'd like to put it up because it ties together Carl Pilkington, genetics, and hobnobs, all of which are great things to have. But right, let's move on to something a bit more serious, an outline of the talk. I'll first start with a bit of motivation, and it feels a bit weird to say this because I'm working with genetics, so motivation is pretty self-explanatory. But there's a couple of problems there that I'd like to highlight mathematically, and how we move on to solve them. This will be sort of the crux of the Wright-Fisher diffusion section. And then I'll end by looking at the exact MCMC framework we've developed to deal with the problem, and show some plots because everyone loves plots. Okay, so what's the story? So you've got Anne, who's a biologist, and she's looking at giraffes. And we all know that selection has been acting on the population of giraffes, and they've been lengthening their necks so that they can reach the trees, the leaves rather, not the trees. But Anne would like to ask the question of, like, how can I model this probabilistically, and how can I extract some information about selection from the model I'm going to generate? In particular, how can I quantify the selection that's happening over there? And so Anne just knows someone, Caroline, who's actually a probabilist, and asks her, "Oh, can you come up with some models for me to model this and all that?" And Caroline's really happy because it's like, "Oh wow, I can look into this and propose some models and all that." And Anne's happy. She looks at Caroline. She asks, "Well, okay, you've given me the models. You understand how the models work, but now I've got data. Can we fit it to it?" And at this point, Caroline gives her a filthy look and thinks, "No, thank you. This is not my job. I'll direct you to someone else." And this is when Statsman enters the picture and saves the day with inference. So this is what I'll be talking about today, about some inference, because I think this is the role of statisticians, right? We want to bridge the gap between the data and the probability models, and to try and bring it closer to actual applications and to understand what's happening there. Okay. So there's these three facets to the problem that we're looking at. Where are we individual in each one? Probabilistically, it's actually in very good shape. There's been a lot of work done on coalescent theory. We start off with the Kingman coalescent that was developed in the 80s. And now we can also talk about lambda coalescence and psi coalescence. And we've managed to incorporate a number of different genetic phenomena there. So we've got stuff like the ASG, which deals with selection, stuff like the ARG that deals also with recombination. So there's a wealth of probabilistic models dealing with coalescent theory. There's also work been done on diffusions, and particularly this centers heavily around the Wright-Fisher diffusion. And nowadays, this is a diffusion we understand relatively well. But there are also more complicated models, right? You could introduce stuff like migration, large jump events where a non-negligible fraction of the population is replaced by a single individual. And more recently, there's been a lot of work that's being done on the seed bank model. And the whole idea there is that you have a population that is weaving in and out of dormancy, and you'd like to understand what the effect of propagation of certain allelic frequency is in that context. So actually, the picture is really good probabilistically. We're in very good shape there. So far as the statistics goes, we're okay. We're also not too bad here. So most of the traditional techniques have relied on what you could call static data, in the sense that they all come from present-day populations. So if you look at something that was developed, say, in the 80s or the 90s, the way of quantifying selection there was always looking at current population frequencies, which is pretty primitive if you think about it, because something like selection is acting over a distinct time frame, right? The longer the amount of time, the longer it has for selection to act. And if you're just going to take the endpoint and look at that and try and draw some conclusions on it, that's going to be very restrictive in what you can say about this selection. I should also mention that there's a sort of an extensive methods that have been developed for coalescent models, and these are usually based on inference for trees. But what I'm more interested in is incorporating these temporal dynamics into inferring selection and so on. And actually, this was in the diffusion literature, at least, this was sort of quite a recent development, because it was only in 2008 that Ballback started looking at this. There have been a number of other papers that have sort of followed up on it and picked up on different ideas. And namely, I should probably mention the Malaspina's paper of 2012, Schreiber 2016, and Beaumont 2019. And this is where we come into play, and we'd like to incorporate these temporal dynamics, but we also have the exactness, which previous methods do not have. And what I mean by exact here is that our method does not rely on any form of discretization. So as I'll be showing in a bit, there's some problems with the transition density of the Wright-Fisher diffusion, and the way most authors have dealt with that is to introduce some discretization. And the framework that we propose, we don't need this at all in any part of the inference. So statistically, we're up to scratch. What about biologically? And actually, this is where we fall somewhat short. There have been massive improvements in DNA sequencing of late, and nowadays we can also sequence entire human beings. But there hasn't been really any sort of aDNA datasets. And what I mean by aDNA is this ancient DNA where you have remains from several thousands of years, and you can kind of string them together to form a time series of sorts. And this is down to the fact that, well, the fossils have been exposed to the elements for thousands and thousands of years. And for you to stumble upon a sample that is big enough that you can look at and has genetic material still in it that has not been degraded over time is already very hard. But thankfully, there's been improvements in the way they do this DNA extraction, and this means that these aDNA datasets are becoming more and more common nowadays. So we're getting there. We're getting there quite quickly. But I would highlight that this is perhaps one of the few fields of science where actually the data is lagging behind to the methods we've already developed, right? So as soon as I saw this, I was a bit perplexed, but yes, it's a bit atypical. Okay, before I move on to our particular scenario, quick one-slide intro to parametric Bayesian inference, because I know that most people here are probably mathematicians. And the first thing that I would like to highlight is this conditional probability that sometimes is called Bayes' rule. And it just tells you that you can kind of change the order of conditioning as long as you post-multiply by the right quantities. And why do I want this? Well, I'm interested in doing inference, which means that I'm going to have readings xi that are being generated by some mechanism, which I shall call a model m theta, and allow this to be parametrized by some vector theta in Rd. And the point is that from these readings, I want to be able to say something about my theta. And the classical frequentist way to look at it was to treat theta as being an unknown, and there is some true theta that you'd like to get to know more about. But in Bayesian inference, or at least in parametric Bayesian inference, the thing is that you want to you want to consider theta as being a random variable itself, and the object of interest is now going to be the posterior. So the posterior is this p of theta given xi, the probability of my parameter taking some values given the data I'm observing. And the way you get the thing on the right-hand side is just simply using this conditional probability up here, right? If you associate theta with A and the xi's with B, you can kind of see where this is coming from and why I've included this constant of proportionality, because I don't really want to marginalize over the data. Look at this top contribution, right? So the likelihood is encoding this. It's the likelihood of having the observations xi, given that my parameter is fixed to be theta, and then I have to post-multiply that by the prior I decided to assign to theta. So let's have a quick example to see exactly how this would work in practice. So if we let xi be the number of silly things that I say in a given day, and we would believe this to be Poisson distributed with some parameter theta, the Bayesian nature of this inference comes into play now, because if you ask me, I'll tell you that theta is always 0, because I think I never say anything silly. If you ask my housemates, they'll probably try and convince you that this theta should be something which is quite large, actually. And the point is that we could both have different priors, and the posterior would be slightly different, but it has been shown that ultimately, as long as you collect sufficiently large amount of data, then you can kind of converge towards the true value, provided that your prior is chosen with a sufficiently large coverage support. Sorry. So then our posterior is going to be given by this expression over here, where because we have a Poisson likelihood, we have this exponential with a theta to the xi on xi factorial, and then we have the gamma contribution coming here. And in this particular case, I've chosen the distributions in a very nice way, so that the posterior is actually a distribution that we know, and it's the negative binomial. In most cases, and in my particular case, this thing on the right-hand side is not going to be available analytically. So there's going to be an added problem in the sense that the posterior is intractable, and we need to see how we're going to deal with this. Okay, so let me sketch out the problem a bit more clearly. In a perfect world, we'd have we would have the whole path that we are interested in. So this is a path of the allelic frequency change over time. So the x-axis is time in thousands of years, and the y-axis is the frequency of allele. And now here we can see how it's continuously kind of evolving. But of course, this is not available to anyone, right? There's no one person who's sat down for 14,000 years tracking how this allele has been changing. This doesn't make sense. What we do have is fossils remains, which allow us to have snippets of what the allele frequency looked like in time. Okay, so what we have to do is we have to rub off the line that joins all those points. And this is what a data set would look like. And well, the best thing we can do is probably just fit a straight line and then use some form of Markov property from the diffusion, underlying diffusion we're assuming, to put in the transition density and look at the contributions of going from this point up to that point in this time interval, from here to here, from here to here, from here to here. So this will be the likelihood that we'll be looking at. It's a product of transition densities, and if you are familiar with diffusions, you'll know that getting the transition density of a diffusion is quite hard unless you have a very specific model. So this will be one of the problems. Right, and given this, we want to say something about the theta. And I'll illustrate what theta is in a minute. The diffusion we'll be looking at is this Wright-Fisher diffusion. And the thing I want you to look at more closely is the drift over here. The diffusion part is just a function of the process itself, and there's nothing of interest there, genetically speaking. What we want to look at is the selection parameter sigma, and the mutation parameters theta2 and theta1. So these will be the parameters we're interested in doing inference on. This will be the triplet I'm interested in. Right, so it turns out that the transition density for a non-neutral Wright-Fisher having selection parameter sigma can be factorized into 3 distinct contributions. The transition density of a neutral Wright-Fisher, which is this first part over here, an exponential, which involves quantities I can compute quite easily because it's just the endpoints and sigma. And finally, we have this expectation, which is a bit of a nasty beast to work with to start. Of course, this is where the obvious problems come up. This is not available analytically. Primarily, this is due to 2 separate reasons. First off, this neutral transition density is cannot be evaluated pointwise. And I'll explain this in the next slide once I'll give you an equation for this P naught of Txy. Second of all, the expectation over here requires knowledge of the entire path xs between time 0 and time t so that I can integrate it. But even if I did have that, it's not quite clear how to go about evaluating this integral or the outer integral, this expectation itself, because this expectation I didn't tell you, but it is over path space. So good luck if you want to actually try and get any kind of tractability there. Okay, so there's 2 problems we need to deal with, this P naught and this expectation here. Luckily, dealing with the P naughts was solved by my supervisors in 2016, where they've actually found a way that you can simulate exactly from a neutral Wright-Fisher, and turns out from the selective Wright-Fisher too. And the point here, so why I said this is analytically unavailable is we have an infinite sum. Right? at any given point, if I want to evaluate this, I need to employ some kind of truncation there. Otherwise, I can't figure out what P naught of Txy is exactly. And if I want to do exact inference, then I cannot rely on evaluating this numerically at any given point. But the composition here suggests a relatively intuitive way from, with which you can use to simulate points according to this transition density. And that's precisely what algorithm 1 is giving. So the point is, if I draw an M according to this Q theta M, I didn't tell you, this Q theta M is a probabilities distribution over the naturals. This BMX of L is a binomial PDF, and this D of theta 1 plus L, theta 2 plus M minus L is just a beta beta PDF. Okay, so these two guys we can simulate from very easily. The hard part is to simulate from this thing over here. But actually, you can utilize a trick that's called the alternating series method to obtain draws according to this probability. Then you can condition on the quantity you draw here to draw a binomial draw. And if you condition on that binomial draw, you can draw your Y according to a beta distribution, which depends on L and M you've chosen. And then you guarantee that this Y is distributed according to the law of the neutral Wright-Fisher diffusion. So this is quite nice, right? But it doesn't tell you how to deal with this expectation here, right? So we have still a more bit to do. But if you think a bit, this rightmost term is actually the probability that no points in a Poisson point process on the interval 0t cross 0 phi tilde plus phi tilde minus lies in the epigraph of this function. Right. So this now suggests an easy way to kind of simulate from this guy now. Because we know how to simulate from this, we can evaluate this exponential very easily. And all we need to do is to check that the points we've generated according to the Poisson point process fall below this graph. So you generate the marked Poisson point process and the neutral Wright-Fisher via the previous algorithm. You check that the points are below this thing. And if they are, then you're happy because you've got a draw from the non-neutral Wright-Fisher. If not, throw that path away, start afresh. Right. And this is relatively nice because all you need to do is just keep on generating the points until you accept one. But that, of course, means that if you have sigma, which is very large, then arguably a neutral Wright-Fisher have a candidate as a proposal, and you're just going to be rejecting a real lot before you accept the path. But then, of course, this is the price to pay to get this exact draws from the non-neutral Wright-Fisher. Okay, but this is all simulation, right? I haven't really told you how I'm going to be doing the inference or why this is actually helpful. And it turns out that if you look at the joint, so if you augment your parameter space by what I will call skeleton points, and I don't have time to go into the details of what these things are, but look at them as just auxiliary random variables, which allow us to get to a tractable, more tractable rather, posterior on the right-hand side. Then, for those of you who are savvy with MCMC, this thing on the right-hand side is presenting itself as something quite nice that we could employ something like metropolis within to get inference about sigma and theta. The only thing that's annoying on the right-hand side is the presence of this Q theta M. But if we're going to update the skeleton points, we can do this using the exact algorithm. I'm not going to go into too many details. I'm happy to discuss with anyone if they'd like to get to know more about this. Conditional on having sigma and theta fixed. We can update our sigma given the skeleton points and the theta. And then we can update the theta given these skeleton points and sigma. So the whole point of this algorithm is going to be we're going to keep on sequentially updating them according to an exact algorithm draw for the first one and Metropolis Hastings updates for the second two. And hopefully the mean and the standard deviation are going to stabilize and we're going to converge, and then we can look at what the posterior over these three parameters looks like. Okay, so I'm slightly running out of time, so I'll move on to the plots. We still haven't applied this to actual data sets. This is kind of the next step we're planning to do. So what we've done is, because I have access to exact simulation, then I've just simulated some data points, got those data points and fed them back into the MCMC to see what the inference is actually telling me. So what I've done is generated readings, 6 if you include the starting point. I've taken a time discretization of 0.1, so what I do is I go 0.1, I simulate a point, start from here, simulate the next point, start from here, simulate the next point, and so on. Where I've taken my selection to be equal to 4 and the mutation rates to be a half each. And I fed this into the Markov Chain Monte Carlo, and this is the results it spat out for my selection coefficient. And, well, I should explain the left-hand plot. The red line, the full red line there is the prior. These circles are the likelihood, and the blue bars are the posterior. And what this plot is telling us is that our algorithm is doing the right thing, because we've started off from this red line. The likelihood has been pulling us towards the right, and this blue posterior is somewhere in between. So it's telling us that, the posterior should always be sort of an interpolation between the prior and the likelihood, and this is what it's looking like. And if you factor in the fact that the true value was 4 and the mean is around about 3 point something, then I think we're doing relatively well. And also the mixing is relatively reasonable. We have acceptance rates of roughly 0.3. So we're quite happy with the inference we're getting for the selection coefficient. If we look at the mutation rates, well, it's a bit more disappointing for the first mutation rate θ1, because as you can see, these blue bars are very close to the red line. So it would seem to imply that we've not really moved away from the prior. But you would expect this, because if you look at the drift contribution of θ1, it's actually a θ1 1 minus xt. And because the path xt has spent a lot of time in the upper half of the interval, this quantity is going to be very small. So there's going to be very little data, the information in the data to make any conclusions about θ1, which is why these blue lines are still very close to the red posterior. And if we look at the mixing, it's relatively good. Some of you might complain that these acceptance rates are a bit too high. And the way I'll deal with that is telling you that I've changed the proposal mechanism there, and the results don't really change that much. However, the picture is more nice for θ2. As you can see, it's a lot more concentrated now. It's gone away from the prior. And, well, this is what you would expect, because now the drift contribution from θ2 is this minus θ2 xt. The bigger xt is, the bigger this contribution, the more information there is in the data about it. Right? So we can be a lot more certain about where our posterior is going to be, and you can see that it's a lot more concentrated between 0.2 and 0.8. And again, the mixing is relatively good. It's a bit too high, but I'll tell you again, I've changed the proposal mechanism there, and the results don't change too much. Right, so that brings me to the end of my talk. I do realize that there was a lot of information to take on. I've tried to make it as sort of laid back as much as possible, but I'm happy to discuss this further with anyone or to take any questions.
Okay, let's get the first round of applause on camera. So if you join me thanking Jaro. Okay, and I stop recording now.